Hello and welcome back to the thrilling world of relativity. Today we're going to do three things. First of all, the drag effect, also known as the flying fish tank. Secondly, the Doppler effect, the relativistic Doppler effect. And lastly, the idea of aberration, which is about the relativity of direction, the idea that the direction in which a light beam travels is relative. So light being dragged by water, Doppler effect for moving emitters of light, and the aberration of the direction of light. So this is all about relativistic optics. We're shifting from relativistic particles to relativistic fields under the ray picture. So let's begin with the drag effect, the so-called flying fish tank. We have our usual pair of inertial reference frames, S and S prime, in standard configuration with respect to one another. And S prime moves relative to S in the, with velocity vector v. Equivalently, because there's no absolute frame of rest, S moves relative to S prime with motion, relative motion vector negative v. But what we're going to do is, instead, if you had a light beam, let's say travelling along the x prime axis, then it would travel at the speed of light according to both frames. But now what we're going to do is have a flying fish tank. We're going to have this fish tank attached to the second frame, attached to the S primed frame. And we want to have a beam of light not in vacuum, but inside this flying fish tank. Now, just to use the previous notation, we have velocity vectors of some object, which would be denoted without primes in the S frame. So the velocity vector would have Cartesian components u1, 2, 3, and according to the S prime frame, the same object would have velocity vector u prime with corresponding primed Cartesian components. Now the question is, the speed of light in S prime, and since we're travelling in the x prime direction, the speed of light in S prime is going to have only a non-vanishing x prime component, and that will not be the speed of light in vacuum, but rather the speed of light within the material of refractive index n. So we know that light does not travel at the speed of light in vacuum in a medium. In a medium, it's slowed down by dividing the speed of light in vacuum by the refractive index of the medium. The question is, what is the speed of this light in a medium when the medium itself moves? Is that light in some sense dragged along by the medium or not? The answer is that light will be dragged along by this medium. And the idea that light is in fact dragged along by the medium, the fact that the speed of light, this light in the flying fish tank, is greater than c on n relative to s, is known as the drag effect, and it was first measured experimentally and then explained theoretically. The experimental measurement was by Fizeau, who constructed a Michelson interferometer with literally flowing water in the arms, and it was first explained theoretically by von Laue, who's famous for his results in X-ray physics, Max von Laue. And what he used to explain the Fizeau experiment was the idea that the Einstein velocity addition formulae, which we derived last lecture. So we want to explain or derive a formula for this dragging of light when it passes through a moving medium. And the starting point is going to be the Einstein velocity addition formula. So the x component of the velocity of this object, this flying light beam in the S frame, is related to the corresponding primed quantity, not by what Galileo would say, which is this, u1 prime plus v equals u1 is what Galileo would say. Instead, we have the Einstein velocity addition formula, which was derived previously, 1 plus the product of these two velocities divided by c squared. So this is the Einstein velocity addition formula, and von Laue said, let's apply the Einstein velocity addition formula to the flying fish tank. u1 prime, as I mentioned earlier, is c on n. v is just the boost velocity, the magnitude of the vector v. And then we have 1 plus the product of u1 prime, which will be c on n times v, which is v, divided by c squared, and one of these c's will cancel. So we want to push this result further. So I'm going to have the denominator 1 plus v on nc to the power of negative 1. Now, the fish tank is not flying at a relativistic velocity. V on c would be much less than 1. Refractive indices are on the order of 1. So I can use the binomial approximation and have the approximation that this negative sign hops down. Next, I'm going to expand this expression, and I'll get 4 terms, first of which is c on n, the last of which is minus v squared on nc. The 2 middle terms I'm going to stick together, and you'll get the following. Now I'll leave the algebra to you, but I stare at this equation, and I've got my eyes on the c's, right? I've got my eyes on the c's because c is a big number. C is a big number. Again, n is on the order of 1. V is much less than c, but c is huge. So I see a term which says that the speed u1 of the light beam in the flying fish tank is to first order, the biggest contribution, the thing which has a c on the top. It's just the speed of light divided by n. Then there's a correction term, and then there's a term which has a c on the bottom. The point is, to an excellent approximation, I can ignore this last term because it's by far the smaller of the 3 terms here. We could give this this thing a name, the so-called drag coefficient. And we get the result that the speed of light in the flying fish tank is the speed of light relative to stationary water plus some drag coefficient that depends on the refractive index times the velocity. The faster the fish tank is flying, the more the medium drags the light along, the bigger the velocity in s. So this is a so-called drag effect. Again, this drag coefficient was measured experimentally by Fizeau before it was explained theoretically, and that middle board is von Lau's derivation. So that's it for the drag effect. I now want to move on to the relativistic Doppler effect, which has cosmological implications because it's used to, it was used to deduce the expansion of the universe, and can also be used, the so-called Hubble's law, and is also used to study quasars, one of the most distant known astrophysical objects. So we want to study the Doppler effect, but from the perspective of relativity. And this is going to be the Doppler effect for an emitter of light. Now, I could imagine an emitter of light as sending out a series of spherical pulses from some source, and that source could be stationary relative to you, or it could be moving relative to you. I could also just have a point source that's glowing light with a particular colour, because that will have a series of wavefronts spaced by the wavelength emitted by this point. Yep. So here's some point just glowing, let's say red light, and there'll be a series of wavefronts propagating outwards, and the separation between adjacent, in this case spherical wavefronts, will be the wavelength. The question is, does that wavelength change? And the answer is yes, it does. If the source is moving relative to you, there will be a change in the wavelength. Now you know this from cars going past you. If they blow their horn, they'll go meow, right? So as they approach you, the pitch of the sound increases. As they recede from you, if I'm over here, as they recede from you, the pitch goes down. So this is due to the fact that the spacing between the wavefronts, as far as you as the receivers are concerned, the spacing between the wavefronts changes by virtue of the relative motion of the source and the receiver. So my voice is slightly higher pitched because I'm receding from you. That effect is also present in relativity. But there's an additional effect. There's two effects in relativity. The first is because the emitter is receding from or moving towards the observer, u, the spacing between the wavefronts is altered. This is one contribution to the Doppler effect that you've met in previous courses. But there's a second contribution to the Doppler effect. Moving clocks run slow. Moving clocks run slow by a factor of gamma. And this is an additional factor that needs to be taken into account when treating the Doppler effect for emitters of light, the so-called relativistic Doppler effect. So we want to consider the scenario I'm drawing now. So we have our inertial frame S with some origin O. We're going to have some point P, and this point P is going to be some point, don't like my diagram, it's going to be some point. So the observer is at the origin O, and there's going to be some emitter moving through some space-time trajectory. Still don't like my diagram. Third time lucky, maybe. So we have some emitter of light, which at some point in time, according to the S frame, will be at a point P. And this emitter at point P is going to be emitting light, which is going to be observed by the observer at the origin. There we go. At a given instant of time, according to S's time, there's no such thing as the time, this object will have some velocity, which I'll call the vector u, all relative to S prime, all relative to S, sorry. This velocity u will have a radial component, again, all relative to the observer at the origin. And so this scalar, which can be positive or negative, is the radial component of the velocity of the particle, which is instantaneously at point P, all relative to the inertial observer fixed at the origin of S, origin O of S prime. Now, as far as if we have a second frame of reference which is actually rigidly attached to the emitter, the emitter would say, I'm an emitter of light, and the emitter would say, I'm emitting light, or a series of spherical light pulses, which have a period of dt naught between them. Here I'm using this notation, rather than priming it, I'm putting a naught on it. This is the proper period of the light that's radiated by the emitter. So if I'm the emitter, I'd say that the period between light pulses is dt naught. Equivalently, the period of whatever wavelength I'm emitting is dt naught. This is the proper period. We want to ask the question, what is the period between the pulses according to the observer at point O? What is the period between the pulses according to the observer at point O? Now, I mentioned earlier that there's two effects. The first is the spacing between the wavefronts will differ from its original value, from its rest frame value, by virtue of the motion of the source away from you or towards you. Secondly, due to the relativistic time dilation. So I'm just going to write down the answer and then explain it. So dt is the period between the light pulses according to the observer at O. There's two effects. The first is moving clocks run slow by a factor of gamma. So I'm taking dt naught and multiplying it by the gamma factor, and the scalar u is not the boost velocity v, it's the magnitude of the vector u, the magnitude of the velocity vector of the point P relative to O. So this is the moving clocks running slow by a factor of gamma. Now I need, and that's where the relativity comes in a sense, and the only place that the relativity comes in is this moving clocks running slow. But there's also an additional spacing between the wavefronts due to the radial motion. Yep. If I increase the radial distance between one emission event and the next, there's an extra radial distance that needs to be travelled, and it's radial distance that matters, right? Extra radial distance that matters. Now remember that time equals distance over speed. So there's going to be an additional time. So let's imagine that UR is positive. Then there's going to be an extra time lag due to the extra distance, the extra radial distance travelled by the source at a given speed. If UR is negative, this will still work, provided I work with signed scalars. So I want to add an extra time lag due to the radial motion, and I know that that time lag is going to be the radial distance travelled divided by the speed of light. What is the radial distance travelled between two emission events? Well, the radial distance travelled during two emission events will be the velocity. That's a radial velocity. Again, the numerator is the radial distance travelled between two emission events, as judged by this observer O. That'll be the radial velocity times the time between emission events. And the time between emission events, we just argued, is gamma dt naught. So this numerator, again, is the distance travelled between two successive emission events emitted from the point P, but all relative to O. We divide by the speed of light. There we go. So I can factor out a gamma of U, which I do now, dt naught plus UR dt naught on C. What I want to do now is to divide both sides by dt naught. Divide both sides by dt naught. This will become a 1. I'm also going to use the fact that the ratio of the periods is a reciprocal of the ratio of the frequencies. I use nu to denote frequencies. Again, to repeat, the ratio of the periods is a reciprocal of the ratio of the frequencies. So we learn our final result, which is that the ratio of the proper frequency of the light to the observed frequency of the light, as observed from the observer O, looking at the moving emitter, we'll have a gamma factor, which is a function of the speed, and I'll write that explicitly as 1 divided by u squared on c squared. U is the speed. We have 1 plus UR on C. So this is the key result for the relativistic Doppler effect for a moving emitter of light. Now, I want to take a special case of this, and this is for radial motion, purely radial motion. And if the motion is purely radial, if the vector u in this diagram points radially away from O, then the radial velocity will equal the speed. Let's have the case of recession. Yep. UR will be U. This is for purely radial recession. On the other hand, if we have purely radial approach, then I'd make one of these a negative of the other. This is purely radial recession. So if you have purely radial recession, and this is a special case, what will that formula become? Well, UR and U become the same thing. So I have the numerator as 1 plus UR on C, which I'll write as the square root of that squared for reasons that will become clear in 5 seconds relative to U. I want to factor what's in the square root as a difference of perfect squares, 1 minus U on C over 1 plus U on C. But U and UR are the same thing. So the U becomes a UR, and one of these square roots cancels this thing. So what we get is our result for radial motion, in fact radial recession, that this ratio of frequencies is certainly not 1, but rather is 1 plus UR and C over 1 minus UR and C. I won't put a box around this because this equation is less general than the boxed one. Now, a very famous example of this formula is an astrophysical application, that if you have some galaxy, this is my impression of a galaxy, its the light that it emits is pretty much a continuous smear. So if you were to have some spectrum, some spectrum of light, for example, you pass this light through a prism and you end up with essentially how much of each wavelength you have, you pretty much get a continuous smear. And the reason is that these emitters in this galaxy consist of a great series of different atoms radiating many different lines, but they also have many different velocities because these things are hot, giving all these Doppler shifts, and you get pretty much a spectrum which is a continuous smear. So this might be what you actually see on a piece of film when you pass light from a galaxy through. So if there's no cold gas around it, this is what you would see on your film when you pass that light through a prism. Yep, so we've taken the light, we've passed it through a prism, and this is what you see on the film. Yep, the spectrum, which is a continuous smear. But galaxies are not exist in isolation. They're actually surrounded by cold gas halos. And these halos of cold gas, because they're cold, they're not moving with as many different velocities. They actually have very well-defined absorption lines. And when I say cold, I mean this in a relative sense. So these absorption lines might correspond, for example, to ionized calcium. Ionized calcium is a particularly strong absorber and will pull out the so-called H and K lines. I don't remember what order they go in, but the so-called H and K lines would pull out or absorb very strongly two particular characteristic wavelength bands. And the separation between these in wavelength space tells us that this is absorption due to ionized calcium. But because of the relativistic Doppler effect, these spectral lines are shifted, and by the shift of the spectral lines, one can measure this object under the assumption of purely radial recession and hence deduce the recession velocity or the recession speed UR. And one of the first people to do this was Hubble, who discovered Hubble's law that the recession velocity was proportional to the distance between us and the astrophysical object. In fact, that's not quite true. Hubble's data was so crap that he actually had no right to make that deduction from his data. But subsequent experiments have verified Hubble's law that the recession velocity determined using this argument is indeed proportional to the distance. Now, the most distant known astrophysical objects are known as quasars. They're among the brightest, if not the brightest, objects in the universe. For quasars, quasars can have truly relativistic recession velocities. Quasars are sufficiently bright that you actually observe the emission lines rather than the absorption lines in the spectra, but the most distant known quasars can have the ratio of these frequencies changed by factors of 8 or more. Yep. This corresponds, for example, to a shift from light which is in the ultraviolet regime all the way down to the red or the infrared. So this has profound cosmological implications, and the key point is this discovery of Hubble's law was a key moment in the evolution of our understanding of the universe, where we realised that it was expanding, which was a shocking discovery and a beautiful one as well. But secondly, I just want to make the point that we scratch things on blackboards, but it's magical, well, in inverted commas, it's magical that you can actually make a connection between these scratchings on blackboards and real data and to actually analyse them and discover surprising things about our world. On that slightly philosophical note, I'll move on to section 18, which is on aberration. And so aberration is about what you might call the relativity of direction. So if you're driving in a car and it's raining, the angle with which the raindrops strike a horizontal surface of the car is going to be dependent on the relative motion of the car relative to the Earth. Let me draw a diagram. So we're talking about aberration. A perhaps more informative name would be the relativity of direction for light beams. Yep. But the point that I've made is that if you're in a car, this is a picture of a car moving with some velocity v relative to the road. Then if it's raining, you could ask the question, what is the angle with which the raindrops strike the car? The question's ambiguous because direction is relative. The faster the car goes, the bigger this angle will be perceived as. So we have the relativity of direction for raindrops, but we know that raindrops travel at non-infinite speed. We have good intuition for the fact that raindrops travel at non-infinite speed, but as always we have poor intuition. Before we take relativity courses, we have poor intuition for the fact that light does not travel at infinite speed. All this is trying to motivate the question, what is... let's examine the relativity of direction for light rays. Yep. So if we have some light ray coming in, and here I'm going to have the light ray coming in according to frame S. That light ray is coming in and it's travelling in the negative x direction. And we ask the question, what is this angle? And S would say that the angle is theta, but we have our S prime frame, the usual standard configuration. And we could ask the question, what angle, theta prime, does S prime ascribe to that light ray? And in general, they'll be different. Our experience with raindrops suggests that they will be different. The purpose of this section is to calculate the difference. So the relativity of direction. Now, to begin with, I want to just define a few quantities. U prime is going to be the velocity of the light according to S. And S would say that in the x direction, U1, the x component and y component, we're ignoring, we can safely ignore the z direction here. The x component will be minus, because it's travelling in the negative x direction, c cos theta. U2, it's also travelling in the minus y direction, will be minus c sine theta. And I would write down a similar relationship for u prime. C is the same, yep, but the thetas in general will be different. So all I've done is to stick primes on the theta but leave the c's alone. Einstein's law of light propagation, the speed of light is c in all frames. But we want to study this relativity of direction. So we take one of the Einstein velocity transformation formulae. Again, this is nothing, well, it's the first member of the Einstein velocity transformation formulae, but I just want to remind you, what I've just written is actually the inverse of this equation here, and I'll remind you that because there's no absolute frames of reference, if you take a valid relativistic formula and interchange primed and unprimed quantities and replace v with minus v, you get another valid formula. So this could be obtained directly from this via the so-called v reversal. Just to repeat, any valid relativistic transformation can be turned into another valid relativistic transformation with a two-step process, interchange primed and unprimed quantities and replace v with minus v. Now I stare at this formula because I want to use it to work out this relativity of direction, to work out how to transform between theta and theta prime. Yep. So u1 prime is going to be minus c cos theta prime. u1 is minus c cos theta. I've just used these two things here. We need to subtract v and divide by 1 minus the product of each term in the numerator, u1v, which will be minus c cos theta times v divided by c squared. And if we divide through by minus c is gone. We divided through by minus c, so this has become cos theta. We divided through by minus c, so that becomes plus v on c. 1 plus cos theta v divided by c. One of the c's cancelled. So we get this expression here. Now that was obtained by considering the x/x prime component, the first member of the Einstein velocity transformation formulae. Similarly, you can look at the second component, and what you'll learn will be that sine theta prime equals some formula. Now, I say some formula flippantly, but I actually have something serious in mind that, sure, we're sitting here calculating something, we're working towards an answer. I call this some formula because I can't really get much physical intuition for what's going on here beyond what I know about Einstein velocity transformations. That might beg the challenge. If you stare at this hard enough, can you stare at it hard enough until these equations become physically self-evident? Or would you say, nah, the problem's not with me, the problem's with the equations, I'm staring at it and it's not talking to me. It's not talking to me because it's not in a suitably simple form, a form that makes its physical meaning suitably transparent. Question, is this an ugly equation in the sense that it doesn't speak to you with physical transparency? Or are you the problem, that you're not staring at it hard enough until it talks to you physically? This doesn't talk to me, maybe it talks to you. Anyway, I want to transform this equation into a form that I think is more physically transparent. Now you'll need to make use of a trigonometric identity, one of the lesser known trig identities. Which is this one. Now using the pair of braced equations, the two bottom equations of this panel, plus this, and with the magic of exercise 25, you'll get the following formula, which relates the angle theta prime to the angle theta. Now, if this were true, then theta would equal theta prime. But it's not true. There's a factor that appears, a dimensionless factor, which is a ratio of velocities. And so this is the so-called aberration formula that relates these two angles. Now, perhaps unsurprisingly, theta doesn't equal theta prime in general. Moreover, if you were to take the speed of light formally to infinity, this square root will become 1. So direction for light beams becomes absolute if the speed of light is formally taken to infinity, or it's taken to be infinitely larger than the velocity, or arbitrarily larger than the velocity. Now, this is the only time in the course that we'll talk about world pictures. Remember, I drew the distinction between world pictures and world maps. World pictures are what a given inertial observer sees at any instant of their time. But what you see at any instant of your time is actually a very complicated amalgam of events that are progressively further in the past. If I look at the moon against the backdrop of stars, I'll see the moon, as it were, a touch over a second ago, but I'll be seeing the stars, according to my time, the stars as they were many thousands or tens of thousands, etc., years ago in my past. So what you see at any instant of time is a complicated amalgam of events that occurred progressively earlier in the past, according to your approximately inertial frame of reference. This makes it even more complicated because the angle with which light beams strike your eye is relative. It's relative on the motion of the emitter relative to you. So colour changes, the colour of the light changes, which is what we learned in our relativistic Doppler formula, but the direction of the light changes. So not only do objects change colour, so I've been thinking about my shoelace, which I really have to do up. Not only do objects change colour, please don't video that. Last time I asked someone not to do something, I was doing a back of the envelope calculation, and I said 1 is approximately equal to 2, but don't quote me on that. It then appeared on the internet forever. Back to the main thread of the argument, the relativistic Doppler effect makes the point that moving emitters change colour. This adds something even more interesting, which is that moving emitters appear distorted because of this relativity of direction. when you, as a physicist, look at something, you receive some light, yeah? And if the direction with which that light travels relative to some axis, let's say your s-axis, x, if direction is relative, then you'll perceive the apparent position of points on the object to be distorted because of this relativity of direction. And so this leads us into very, very nice cartoons, one set of which is calculated by Leo Braun from Monash Mathematical Sciences. So if you ask the question, suppose that the speed of light was 60 kilometres an hour, or suppose the speed of light was 20 kilometres an hour, what would the world look like to us? That would be a world, by the way, where we would have excellent intuition about the non-infinite nature of the speed of light. Question, what would the world look like if the speed of light were much smaller than it is? So Leo Braun has these beautiful videos. For example, if you fly past a black hole, not only do you have special relativity effects, but also general relativity effects. So if Doctor Who's TARDIS were to fly close to a black hole and you were to observe it, what colour distortions and what visual distortions would you see? Please look up Leo Braun, Monash Mathematical Sciences, and you'll find those videos. There's another set of researchers, Savage and Searle. If you search for those names and look up the words relativistic ray tracer, they will also give you some videos of what the world would look like if the speed of light was, let's say, 60 kilometres an hour. And as one example, we have a tram. So suppose that we're looking at a tram. By the way, the tram is chosen deliberately because Einstein thought a lot about trams when coming up with relativity. And we're actually looking at the tram from above. Yep. So we're sitting on, let's say, a 10-storey building looking down on a tram that's moving along some tram tracks. Let's say in this direction. And here's a lamp post. So this might be, let's say, a 3-metre tall lamp post casting light down on the tram. Now, if the speed of light was infinite, you would expect that the shadow of the tram would have a particular shape. So you might expect, let's say, the green trace, which is the shadow that you would get if the tram was stationary relative to you. So this is the tram, and this is the shadow of the tram due to this lamp. But the speed of light is not infinite. The shadow is going to be distorted by virtue of the motion of the tram. And the distortion is quite striking. Yep. You'll get something like this. And how do they calculate these movies? Well, they take our formula here. They'd say that the moving tram is basically a series of points in space-time, a series of events. So if I was to draw a dot on the tram, that would be a series of events as it moves through space-time. Fair enough. You could imagine the light beam bouncing off that point. You might have a red photon bouncing off a bit of red paint. It's bouncing off. You could do angle of incidence equals angle of refraction. You might need to take some relativity into account there, but the light would bounce off. And then it would take finite time to travel, and you would have the relativistic aberration formula to take into account. And using this formula, you could work out the distortion of the shadow. And they do this. This is the equation that goes into these relativistic ray traces. If you want to calculate how colours change, you would also need to take the Doppler effect into account. I invite you to stare at this picture until it makes perfect sense. I'm not going to explain why the shadow is distorted in this particular way, other than to say that the speed of light is not infinite, but I invite you to think about this. Now, this is a key moment in our course. It's a key moment because we are about to get much more sophisticated by introducing the language of tensors. So I've mentioned many times before that physical laws by the relativity principle have the property that they are the same in all inertial reference frames. The laws of physics are the same in all inertial frames. Therefore, the laws of physics should have the same mathematical form in all reference frames. And that demand that the laws of physics should have the same mathematical form in all reference frames is a very, very powerful constraint. It also, on physical theories, any physical theory that does not have the same form in all reference frames, in all inertial reference frames, is not going to be considered acceptable from the perspective of relativity. General relativity takes an even more hardline perspective. It says what's so special about inertial reference frames. The laws of physics are the same in any reference frame, is a statement upon which general relativity begins. But for the purposes of special relativity, the laws of physics are the same in all inertial frames. Therefore, the form of the laws of physics, for example, differential equations, must be the same in every inertial reference frame. Now, the mathematical formalism that has of having the same form in all inertial reference frames is that of tensor analysis. So we have a business, which is a very ambitious one, of looking with scrutiny at every single law of physics that we know of and saying, can it be tensorialized? Can it be expressed without change in tensor form? If the answer is yes, then it's going to be acceptable to us. And if the answer is no, it's not going to be acceptable to us, and we therefore need modification. So, for example, Newtonian mechanics cannot be expressed in a form that's unchanged under Lorentz transformations. The transformations we care about are Lorentz transformations here, Lorentz transformations which re-coordinatize space-time. Do the Newton equations change in form? If you make a Lorentz transformation, the answer is yes. Therefore, the Newton equations are unacceptable. Do the Maxwell equations change in form under a Lorentz transformation? The answer is no, they don't, and we'll prove this. That's not at all obvious from the grad-div curl way that you've written Maxwell equations before. By the way, they're very complicated equations because they're written in a very untransparent way. We'll learn that the Maxwell equations can be written in tensor form without modification, that they are, in fact, one of the simplest equations that can be written down that are invariant in form under the Lorentz transformations. And that last point I want to emphasise is that of simplicity. This is level 3 theoretical physics, so it's a hard subject. On the other hand, there's a profound simplicity that's emerging. And that profound simplicity is once you get your head around tensors and you demand the tensor laws be written down, or else they're not acceptable because they have the property of being the same form in all reference frames. You can start asking very profound things like, what are the simplest physical laws I could possibly write down? What are the simplest physical laws I could possibly write down that are consistent with the relativity principle? And the somewhat shocking answer is that you could write down 4 or 5 of the key equations of physics. Einstein field equation in vacuum, D'Alembert wave equation, Maxwell equation, Klein-Gordon equation of relativistic quantum mechanics. You could write it down in about 20 seconds in retrospect by just asking the question, what are the simplest field equations that we write down that obey the relativity principle? And that's a very, very profound simplification, one of the most profound in physics. This is what we're working towards. But in order to do so, we need to introduce the language of tensors, and this is difficult. I found the idea of tensors the most difficult concept in mathematical physics at level 3. In fact, it's pretty hard even beyond that. So it's a difficult language, but that doesn't change the fact that it actually leads towards a very, very powerful, profound simplicity, one of the most profound simplicities in physics. For those of you studying fluid mechanics, tensors are not just applied to relativity, and for 2 reasons. One is relativity applies to all physics ultimately, but tensors are also used in other areas of physics, including fluid mechanics. For those of you who are studying or will study fluid mechanics, you'll encounter tensors. They're also used in various areas of engineering and more broadly. In the next class, what we're going to do is step aside from discussing relativity per se and discuss Rindler's introduction to tensors for special relativity. This is the appendix from Rindler's book, which we'll go through. We'll pause, have a mathematical aside where we spend about a lecture developing the machinery of tensor analysis, which we'll then go forth and apply to our physical laws. In particular, we'll revisit some of the previous calculations from a purely tensorial perspective, but then we'll be able to go much, much further. That's it for today. Thank you.